Hello everyone, my name is Sampa Biswas. I'm a professor of AI&DS department of St. Peter Engineering College. So today we are going to discuss about the expert system subject, and the topic we will cover the introduction to the artificial intelligence. So everyone nowadays everyone is using the artificial intelligence, and everyone is familiar with this, right? So now come to the artificial intelligence. Artificial intelligence, if you break down the term, that is the artificial and the intelligence, right? So what is the meaning of artificial is the man-made thing, right? And what is the meaning of intelligence is the ability to acquire knowledge and understand and apply the knowledge to achieve the goal or to take some decision. So now just combine both the term, that is artificial intelligence, right? So basically if we put the intelligence to an artificial or man-made thing, and if that system or that device is having the capability of taking decision, that time that system or that device is known as the artificial intelligence device, right? So if you just go through the definition of it, then artificial intelligence, you can see here, the artificial intelligence is the capability of computational system to perform tasks typically associated with human intelligence, and such as learning, reasoning, problem solving, and taking decision. So that is basically known as AI or artificial intelligence. Now for the first time, John McCarthy coined the term in 1956, and he is known as the father of AI. Okay, and now come to the history of AI. So at the you can see here in the diagram, you can see in the 1943 the evolution of artificial neurons. At first it came, okay, and after that the Turing machine, it came on the 1950. After that, in 1956, birth of AI, okay, that came. And after that, in 1966, the first chatbot, that is Elisa, it came, and that basically introduced. And after that, the first intelligence robot, that robot 1, that thing came in the 1972. And after that, the first AI winner, that is basically come on the 1974 to 1980. In that period of time it came. And after that, the expert system is basically comes in 1980. And after that, you can see in 1987 to 1983 the second AI winner came, okay. And after that, in 1977, that IBM Deep Blue, the first computer basically invented. And after that, in 2002, AI in home, basically that smart home kind of thing, that time it came. And after that, in 2011, the IBM's Watson quiz show that basically happened that time. And in 2012, the Google, now Google we are using nowadays, that thing basically came in the market. And after that, in 2014, the chatbot basically, nowadays we are using chatbot, that thing basically invented on 1914. And after that, in 2015, the Amazon Echo, that is another evolution of AI, that thing came. And after that, in 2020, in 2020, that chat GTP came. Okay, so this is the basic history of AI, from the evolution, from the starting of the evolution of AI. Okay, now we have to know about what is agent in AI basically. So agent is nothing basically an programming module, you can say. And in expert system or in AI, agent is basically a programming module. But in real time, if you consider about, if you say about agent is basically agent is that thing that can perceives the environment through sensors and acts upon that environment through actuators, okay. So it means basically agent is that device or that person who can sense the signals or signals from the outside environment, and it can take the action based on the signal coming from the outside. So for example, suppose mosquito is biting on your skin, okay, and that skin, through that skin, the signal, that mosquito biting signal, is going to your head, right? After that, your head is processing something, processing that okay, some mosquito is biting you, and then only you are taking some action. Basically you are hitting the mosquito with your hand. So basically if you just like break down the whole process, so basically you are receiving the signal from the environment, okay, and that signal is going to your brain, and after that we using the actuator. Actually here actuator is basically your hand. Using that you are taking the action. Basically you are hitting the mosquito, okay. So this is basically the fundamentals of agent, okay. And there is three type of agent is basically there. That is the human agent, and this is the basic agent, the human agent, robotic agent, and the software agent, okay. And in this diagram you can see clearly the element or the perception is coming. This is the agent here, okay. And agent is having the sensor, that actuator, and it is receiving the signal from the outside world, and after that it is processing inside its brain, and after that it is basically taking the action, and to the action for that signal, okay. And if you are talking about the robotic agent, for human agent, basically like us, if when some person is taking some action, that time normally that is a human agent, okay. And if you are talking about the robotic agent, that robotic agent is having some sensors like that eye, that camera. Instead of eyes, that robot is having the camera, okay. And that robot is having some like for hearing sensors, that robot is having, okay. Those are basically sensors for that robot, okay. And for the action, taking the action, the actuator is basically the hand of the robot and the leg of the robot, okay. These are the actuators, okay. And the software agent is basically nothing, it is a programming module through which it can it can receive the input from the from the outside world, or from the client, and it can process that on, and it can give the like solution of it. Basically it is the providing the solution of it, okay. So that is the agent in basic. So after that we have to know about the what is the goal of AI, why you are studying about the AI, right? Why you are using the AI? So for that reason you have to know the goals of AI, okay. So AI is basically used to create or develop a machine which can think like a human, or which can act like a human, okay. That is the main goal of AI, okay. That that machine or that device will take the will acquire the knowledge, or will acquire the knowledge, and it will work on that, and after that it can behave like a human, it can think like a human, and it can take the decision like a human based on the knowledge which we are providing to that machine, okay. That is the main goal of AI. And next it can automate the intelligence tasks, okay. Basically for AI we are using basically for solving our problem, or solving the big tasks in a like a easy way. For that reason we are using AI. So it is using for automate the intelligence tasks. Next it is using for improving the accuracy and the efficiency. Basically suppose you want to do some file processing, okay. Basically you want to segregate some data, you want to sort some data from that file, and that is basically very big file, okay. Lot amount of data is having there. So if we want to do it by manually, that time it will take lot of time, okay. And it can there is no guarantee that it will give you the exact result at a time, okay. For that reason if you are using AI for instead of manual task, instead of manually performing the task, that time if you are just training the model and you are just giving the command correctly, that time it can solve the problem very fast, and it will give you more accuracy. For that reason we are using AI, okay. Then after that AI we are using for solving the problem, and for reasoning purpose also we are using AI. Another one is the through enhance the human and machine interaction. Basically for the we have to enhance the basically how the machine and the human is interacting to each other. For that reason we are using AI, okay. And there is some more goals of AI you can see here, to learn from data and from and experience. That is another goal of AI. And to support decision making, basically AI is having the quality of taking the decision, okay. for that reason we are using AI, that is another goal. And to build an intelligent autonomous system, that is also another goal of AI. Okay, now come to the areas of AI. Okay, these are the domain or areas of AI. Basically the first thing is basically machine learning is one domain, you can say, and another one is the basically natural language processing, and then expert system, speech recognition, vision, okay, planning, robotics. These are the areas of AI, you can say. So in under the machine learning there is deep learning is there, right? And under natural language processing, the text generation, question answering, context extraction, classification, and machine translation. These are the areas, sub areas of NLP. And then speech recognition, like basically speech to text conversion and text to speech conversion, that is the sub areas of speech recognition. Then vision is basically machine vision or the image recognition. These are the sub areas of all the domain of AI. Okay, now come to the like search algorithm of AI. Why we are starting about search algorithm? What is search algorithm? So search algorithm is basically just now we started about the agent, right? So agent when the agent is performing any task, for that reason that time that agent have to find for solution, right? Suppose you have you are giving some task to that agent, and that agent have to give you the solution. For that reason that agent have to find for the solution at first. So how that agent can find the solution? For that reason there is many search algorithm in AI. Using the search algorithm only, that agent can find for the solution, look for the solution. Okay, so the search is basically the search algorithm is basically yeah, here you can see a search algorithm systematically explore the this state space to find an optimal or satisfactory solution. That is the main that is the definition of search algorithms in AI. And the search algorithm having some terminologies. Those are basically search, what is search, what is search tree, what is action, what is transition model, what is path cost, what is solution, and what is optimal solution. These are the basic terminologies of AI. Okay, so what is search? Just now I explained. Search is basically when it is looking for some solution. That is simple term, that thing you can consider as search, right? So what is search tree? Basically whatever the problem you are giving to that agent, that problem, when it will explore that problem, so it will basically represent the problem with in some graphical way, or it will represent the problem in some tree like structure. So that is basically where it will perform the search. So that is basically known as search tree. Okay, and next come to the action. Action is basically to solve the problem. Whatever the action that agent is taking, that is basically known as action. Okay, now come to the transition model. Transition model is basically that while performing the searching process on the search tree, so that time the intermediate models or intermediate problem solving steps are basically comes under the transition models. Okay, now come to the path cost. Path cost is basically after finding a solution. So if the path, like whatever the path, suppose for a problem there could be multiple solution, okay, multiple solution, and there could be multiple path for the for getting the solution. Okay, so there is basically whatever the path you are following to reach the goal state. So whatever the steps you have to take, how many steps you are taking, how long time you are taking, so based on that you will the optimal solution or the solution optimal solution that agent will provide to the client, right? So or to the user. So path cost is basically for reaching to the goal node, whatever the path you have followed and whatever the cost you had to do for the cost you had to spend for that to getting the path to getting the goal node, that is basically known as path cost. Okay, and solution is basically, just now I told you, there could be multiple solution, and finding those solution or the solution or that output is basically comes under the solution. Okay, and optimal solution basically what if there among those multiple solution, whatever the solution is accurate, whatever the solution is basically having the least cost. Okay, so that solution and whatever the solution is taking less time also, so that solution is basically known as optimal solution. Okay, now come to the properties of search algorithm. So search algorithm are having two main four properties. First one is the completeness, second one is the cost optimality, third one is the time complexity, and fourth one is the space complexity. If any search algorithm is not like satisfying all those four properties, that time you can't say like that search algorithm is optimal or that perfect for solving any problem. Okay, like, so what is completeness? Okay, completeness is the uh, completeness is basically giving the guarantee to find a solution if there is a solution present in the problem. Okay, so that is basically known as, basically that property is fulfilling the algorithm. Okay, so that is completeness. Another one is the cost optimality. Cost optimality is basically ability to find the highest quality solution, basically ability to find the optimal solution, that is basically known as cost optimality. Okay, and time complexity. Time complexity is basically to finding out the optimal solution, whatever the time that algorithm is needing, algorithm is taking, that is basically known as time complexity. Okay, and if for any search algorithm, if the time complexity is less, that time that algorithm is basically, and that algorithm is giving us a optimal solution, that time we can consider the way that algorithm is good for this problem. Okay, and what is space complexity? Similar to the time complexity, space complexity is basically defining how much memory space the algorithm need to find out the solution. Okay, so these are the main property of search algorithm. Okay, now come to the type of search algorithms. There is basically, in AI there is basically two type of search algorithm is there. First one is the uninformed search algorithm or blind search algorithm, and another one is the informed search algorithm. Okay, so what is the meaning of okay, at first I will give you the breakdowns of it. So in case of uninformed or blind search algorithm, so there is basically, you can see there is many search algorithm is there. First one is the breadth first search or BFS, and second one is the depth first search or DFS. Okay, after that the uniform cost search is another search algorithm in uninformed search algorithm. Depth limited search is another one. Then iterative deepening depth first search is another one, and bidirectional search is another uninformed search algorithm. Okay, and come to the informed search algorithm. Informed search algorithm is basically divided into more categories. So best first search, this is different from breadth first search, that is called best first search. Okay, and A-star search algorithm, and there is some local search also there, that is the hill climbing search and simulated tunneling and beam search. These are basically comes under the local search algorithm. Okay, so and best first search is basically there is two categories there also, that is basically greedy search or A-star search algorithm, just now I explained here. So now come to the uninformed search. So what is the meaning of uninformed search? Uninformed search is basically when the algorithm is when the agent is performing some search algorithm, and that time whatever the problem you are giving to that agent. Okay, so if you are giving some information like whatever the path cost you could need you could need to get the solution, or whatever the time, or basically if you are providing any information prior. Okay, that time that time that is basically known as informed search, basically we are having some information. Okay, but in case of uninformed search, that time we don't have any information. Okay, basically we don't have any idea about the like approximate path cost or node cost or anything, we don't have in case of uninformed search algorithm. Okay, so and in case of uninformed search algorithm, the first algorithm we studied about the breadth first search, right, or BFS. As we already studied in the data structure, we already studied about the BFS. So BFS is basically a search algorithm which search along the breadth of the tree, right, along the breadth of the tree, like this one. Suppose there is a tree, calling about BFS. Okay, BFS. So BFS is basically breadth first search. So suppose there is a search tree is there. Here, okay, suppose this is the search tree is given there, and like we have to perform the BFS on this search tree. Okay, so BFS is basically perform the search along the breadth of the tree, right? So this is the if I just name the give the name to that tree, this is level 0, this is level 1, this is level level 2, right? And suppose the goal node is G. Okay, this is the goal node we have to find out, okay, using BFS. Okay, so when you are talking about BFS basically perform the search along the breadth of the tree. Basically in this direction it will perform the search, right? Along this direction only it will perform the search from the starting node to root node. It from the root node to leaf node it will perform the search. Okay, so as we know, BFS follow the first in first out data structure, right? So how we perform the first in first out, where we can see the first in first out, we see in the queue data structure, right? And how we perform the first in first out, I will show you. Yeah, suppose we want to perform the BFS on this tree. So there is, suppose this is a queue. Okay, suppose this is a queue. So first we have to follow the first in first out, right? First in first out, or FI FO, basically whatever the element is coming inside the queue at first, while we are taking out the element from the queue, that time we will take out the first element. Okay, so suppose when we are talking about that 0th level, that time that A is the root element here, that element there is in that level, there is no other element is there, right? So for that reason we are inserting that first in that data into the queue. Okay, and basically we insert the data from the back side of the queue and we take out from the front side, right? That is the front and back, you know, front and back. So this is the first element we inserted in the like queue. Okay, now we have to we have to follow the first in first out. How we will follow the first in first out? Whatever the element came at the first, we have to take it out. Suppose I'm taking it out, I'm just cutting it down. Okay, now now what we have to do, basically whatever the element we are taking out from the queue, whatever the child node that element is having, or or that node is having, so we have to insert those child node from the back side of the like a queue. Okay, so that thing only I'm doing. Oh, so we already take out the A, so whatever the child element that A is having, that B and C, right? So I'm just inserting B and then C, right? From the back side we are inserting. Okay, now what we have to do, basically again we have to follow the first in first out, right? Again we have to follow the first in first out. So the same thing, whatever the element came at the first to the like queue, we have to take it out, right? So now I'm cutting the B, and again we will follow like whatever the child node that B is having, we have to insert that, right? So I'm just inserting here another level. Okay, so at first the basically we are inserting the data from the back side, right? So at first C was here. See, at first B is having two child node, right? D and A. So in a two space, so D will come here and this is the E, right? This is the next step. I'm just giving the arrow here. Okay, now again follow the first in first out. Now I have to take out C, right? So C is having what are whatever the child node that C is having, we have to insert that, right? But before that only there was some element was there. What are those element? D and E, it was already existed in the queue, right? So and C is having 2 child node, so we have to insert that F and G I'm inserting, and D and E will come here, right? So after that we have to again follow the, because still we haven't found out the goal node, right? So until unless we are finding out the goal node, we have to perform the search. When we will get the goal node, that time we will stop there only. Okay, so now we have to again follow the first in first out. So basically we are taking out D. So D is not having any child node. If it had any child node, that time we can insert from the back of the queue, right? So D is not having any child node. So after like dequeuing the D, what will be the queue? Like the queue will be like this: E, F, and finally G, right? So again we have to follow the first in first out. So now I'm cutting E, right? Now after that I'm going here, that Q is having only F and G, right? So F and G, right? Now again we haven't found out the goal node yet, so again we have to perform the same first in first out. Now I'm just giving here, now that F and G, I'm just cutting down F, and finally it will be G there, right? Only G will be there. So G is the goal node, right? So when we are finding out the goal node, that time we will stop the like search there only. Okay, in BFS we will stop the search there only. If that if there is more child node of other node was there, that time also if we find out the goal node, that time only we will stop. Okay, now just I'm just taking when I'm getting the goal node, that time I'm just also taking the goal node. Okay, so this will be the solution. So if we just write down the path, whatever the path we followed here, if we write down the path, I'm just writing here. Once again, I'm writing here. The path is basically whatever path will be here. So whatever the element we have take out from the queue, we have to follow the same order to write down the path. So at first we took out A, right? After that, what we took out? We took out B. After that, sorry. After that, we took out C. Then we took out D. Out D. Then we took out E. Then we took out F. And finally we got G, and G is the goal node, right? So this is the path of the problem. Basically finally we got the goal node, right? So now just if we just follow the path, and if you just compare with the tree, that time you will know how why we are calling it as BFS, or why we are calling like it is performing the search along the breadth of the tree. Okay, so what is the element at first? The first element is basically that A, right? So this is A. Okay, after that, what is the element in the path? That is B. Basically from here we are coming here, right? We are coming here. After that, B, what is that element? We are basically going here. After that, what is the element? D, right? So we are basically coming here to here, right? After that, what is the element? D, after D is E, then F, and then finally we got G, right? So you just compare the path and the tree. Basically we are for a single level, at first we are performing the search along the breadth of the tree, then only we are going to the next level, right? So for that reason, as we are performing the search along the breadth of the tree, for that reason only it is known as BFS, or best first search. Okay, so this is the thing. And now come to the, yeah, so this is basically how we are performing the FIFO in the search tree, and we are getting the optimal solution here. Okay, so now come to the what is the previously I told you about the properties of search algorithm. So another is search algorithm property for the breadth first search is basically the time complexity is here, order of B power D. So B is the number of branch factor, okay, or the number of node in the same level, you can say, and D is the depth of the tree. D is the depth of the tree, and space complexity is also same here, order of B power D, and completeness is basically is a complete algorithm, okay. It will give you a solution if if there is any solution exist for the problem, it will always find out the solution and it will give you the solution. For that reason BF is known as complete algorithm, okay. And optimality is basically BF is optimal also if the path cost is not is a sorry, BFS is a optimal algorithm also, okay. Here you can see BFS is optimal if the if path cost is a non decreasing function for the depth of the node, okay. So BFS is basically a complete like algorithm. Now come to the example. Here I have mentioned same different example. You can just perform the same FIFO in this example also, and this will be the final path for the problem, okay, and this will be the final solution. After that, now come to the advantage and disadvantage of like BFS. So BFS advantage, you can see here, BFS is providing a solution, okay. If there is any solution existed, then BFS will always provide you, okay, and it will provide you the minimal solution or the optimal solution always. That is the main advantage of BFS. There is other advantage also, but this is the main, okay. And disadvantages, there is basically it will require a lot of memory because it is exploring all the level of the tree and whatever the all the node of the tree also, okay. For that reason it is basically require lot more amount of memory, okay. And BFS need lot of time also because just now I said it is exploring all the level of the tree and all the node of the tree until unless it is getting the goal node, okay. For that reason it is taking the time complexity and the space complexity is more here, okay. That is the main disadvantage of this algorithm. Now come to the application of BFS. BFS is basically we are using for many purpose. So I'm just giving you two example. Like for GPS navigation system we can use the BFS, and after that for network broadcasting also we can use BFS, okay. So this is the complete BFS algorithm. I hope it is clear to everyone. Now come to the DFS, okay. So DFS is basically known as depth first search. By the name only you can see depth, basically it will search along the depth of the tree, right. I'm just clearing here. It will now come to the, just give me one second. Okay. Now we'll talk about DFS. Performing the same like on the same tree only I'm performing the DFS. Okay. So you see here like previously the BFS was following the first in first out, the queue data structure, but the DFS follow the last in first out, and where we see the last in first out in the stack, right. The stack data structure, we can see the last in first out. Basically whatever the data is coming at the last, that data we have to take out first, okay. That is the LIFO. And the time complexity and space complexity I have mentioned here. After, yeah, the time complexity is basically order of order of B power m. Sorry, this will be order of B power m. Okay, I'll explain those things later. So at first I'll show you the example, okay. So if we follow the LIFO or last in first out in the tree, that time how we can perform the algorithm. So this is basically last in first out performing. out follow. So in the queue data, sorry, the stack data structure, we follow the last in first out. So suppose this is a stack. So in that stack only we'll perform the uh, we'll perform the DFS using the using the problem, and we'll find out the goal solution. Here also the solution is same, the G we have to find out. Okay, so suppose this is a stack, and in a stack we perform two operation. What are the two operation? Push and pop, right? Push means basically for insertion of any element we perform the push, and for deletion of the element we perform the pop, right? So what is the what is the formula of push? Is basically sp is equal to sp plus 1 for pop will be which plus 1. Suppose if the structure is empty, that time sp will uh, sp suppose that time sp is denoting here. Okay, so we have to insert the element in the stack. So whatever the first element here, that a is the first element, suppose I'm inserting that one the stack. Now we have to perform the last in first out. Whatever there is only one element is there, so we have to take it out. So I'm taking it out. Now again we will perform the same thing previously how we perform. Whatever the element we are taking out, whatever the child node that element is having, we have to insert that child node into the stack. Okay, so now I'm just inserting the child node of a is having two child node b and c. So I'm just inserting that b and c here. Okay, now what we have to do, we have to again perform the last in first out. Whatever the data came in the at the last, so that data we have to take it out first, right? So I'm just cutting down b here, and whatever the like whatever the child node of b we are having, we have to insert that one. Okay, now see, previously the c was here only, right? And in case of stack, whatever the element we are inserting, that will always come at the top, right? So for that reason, previously the c was moving the place, but here the c, whatever the place of c, it will be there only, but whatever the data is inserting we now, so that data will come at the top, right? So we have to d and e will come here, right? Again we will come here. Now again we will perform the like a last in first out. So what will be the, so this will be the structure basically. So d we are taking it out, so e and c will be there, and if the d is not have, as d is not having any child node here, so for that reason we will not insert anything. Now we will insert e here. Okay, basically we will perform the LIFO, and we will insert uh, as e also not having any child node, for that reason we are not inserting anything. So c is there, right? So now we have to take out c, and c is having child node, right? C is having f and g, right? So we are just inserting f and g here, f and g, and finally we are taking out f, and finally g will be there, right? So this is basically, this is how we perform the last in first out in uh, like in a in a stack, right? So now just just find out the path how we are getting the solution of g, right? So path will be, here path will be whatever the element we take out first, we have to follow the same path here again. So at first we took out A, after that we took out B, then we took out D, then we took out D, after that D we took out E, then we took out C, after that we took out F, and finally we got G. This is the goal node, right? So this is the final path for the solution, for the problem. Okay, final solution for the problem. So just again just compare that path with the tree. Now we can just compare it. So at first we went to the A, okay, and after that we went to the B, okay. Now we went to the D, right? We here we went to the C. So basically if you just follow the path here, that time only you can say the algorithm is basically working along the depth of the tree, right? So the depth of the tree, the algorithm is working. So after that, basically after coming from here to here, then here to here, we are basically going after D we are going basically E, right? So we can't go from here to here. Here we have to do the backtracking, and again we have to come here, okay. This is the path here. After E we are going to C, so we just can't go directly here. We have to do the backtracking, we have to do the backtracking again here, and finally we have to come here, okay. This is the C. After that C we are going to F, and then we are going to G. We can't go directly here, basically we are going back, and then we are going to G, right? So this is the path here, and this is how basically the algorithm is working here, and for that reason only it is known as depth first search, or depth, basically it is working along the depth of the tree. For that reason it is as depth first. Got it? So yeah, so now come to the time complexity of DFS. Basically the time complexity is here order of time complexity be order of b power m, order of b power m. So m is basically here you can say maximum depth of any node that and it can be larger than D, okay. So m is that, and space complexity is basically here you can see order of b into m, okay. This is the time and space complexity of DFS. Now come to the completeness. So DFS is basically a complete algorithm within a finite state space, okay. Basically if if it is a limited tree, if that limit is basically known, that time DFS is a complete algorithm. That time only it can find the solution. But if the limit of the tree is infinite, that time DFS can't give you the guarantee that it will give you the solution, okay. Now come to the optimality. It is basically non-optimal. As I said, it always don't guarantee you the guarantee that it will give you the solution of the problem, okay. For that reason it is non-optimal, okay. Now here also again I explain, I give some other problem here. You can also follow the first LIFO. You can just apply the LIFO in this algorithm and in this tree, and you can find out the solution here. So now come to the advantage of DFS. So advantage is basically requiring less amount of memory, okay. That is main advantage, and less amount of time also, that is another advantage of like DFS. And it help you basically here we are doing the backtracking, right? So doing the backtracking, you have to store the data also, right? For that reason only it is like it is saving the data also, okay. So and disadvantage is basically there is no guarantee of finding out the solution. If the, as I said, if the tree limit is length is very long, that time it can stuck like it can stuck in that like in the limit only. It can't give you the guarantee of getting the solution, okay. And sometime it may just now I said sometime it may go in the infinite loop, okay. And it doesn't yeah, it does not find out the shortest path for the solution. These are the disadvantage of DFS. And now come to the application of DFS. Basically, for finding out the strongly connected components of a graph, we use the DFS. Basically, like strongly connected for the directed graph, basically we use this DFS, and for web crawling basically we use, and for model checking we use DFS. Okay.